I'm giving you 5 minutes time to just see it, because you should understand, like, and you need to make a picture in your mind, like how this roll pitch axis is. What does this mean? Okay. Shivam, Shivam, where are you?
Yes, sir.
बताइए, समझ में आ गया कि कोई डाउट है?
नहीं सर, आ गया सर.
So, what do you mean by YIMU, the pitch axis? How you can define it?
Sir, YIMU.
Pitch axis means up and down. Okay. When
Okay, sir.
aircraft is uh, uh, when aircraft is doing maneuver up and down, it means it is performed along the axis that is going through the right wing. See, up and down motion is performed about an axis, so that axis will be towards right wing. Left and right can be performed about the axis that that is crossing towards downward. That is crossing the aircraft and going towards downward. About that axis only the left motion can be performed. Okay. So this is the reason why I told that this XIMU direction is towards the direction of XIRS, but still there is some differences. The axes do not coincide. Okay, it differs in terms of some angular biases, but that biases is very low. Okay, please mute. Now we have discussed two coordinate system. The third one is associated with the, I write over here, first coordinate system is associated with laser scanner. The second is with respect to IMU, and third is with respect to GNSS antenna phase center. Okay, we'll call it ETRS, or tangential reference system. Is defined as tangential reference system. So again, it is defined with respect to Earth, North Pole and South Pole. Okay, somewhere it's locally defined on the surface of Earth. So its x-axis is towards north. You can say this x ETRS towards North Pole. Z ETRS is towards center of mass of Earth. CME stands for center of mass of Earth. Okay, so Z axis will be towards center of mass of Earth. Okay, and again it is a right-handed coordinate system. So Y ETRS is calculated by using right-hand thumb rule. Right-handed system. Okay, so this is the third and fourth coordinate system is related to the Earth surface itself, and that is ECEF, Earth-centered fixed coordinate system. Who will tell me how to define ECEF? We have already discussed about ECEF many times. Sumit, please unmute. Sumit, where are you? Alok.
Yes.
Let me know how to define ECEF.
Sir,
We already discussed in our previous lectures.
सर वो ओरिजिन सेंटर ऑफ मास को, अरे अर्थ के सेंटर ऑफ मास को सर ओरिजिन लेके लॉन्गिट्यूड, लैटिट्यूड और एल्टीट्यूड में डिफाइन करते हैं सर पॉइंट.
The first point is correct. Center of mass of Earth is taken as origin in ECF. And how to define direction of axis?
Mhm.
Listen carefully.
हाँ
Okay?
सर 1 मिनट सर जेड एक्सिस को सर अर्थ के रोटेशन एक्सिस से पैरेलल लेते हैं और
It's North Pole,
हाँ
towards North Pole. Okay?
ठीक
So that is ZECEF. Okay? X axis ये क्या है? This is center of mass of Earth, and this is a prime meridian. Okay? This and this is equator. Equator, and this is prime meridian. And this is the intersection point. So the line crosses through center of mass of Earth and this intersection point. It is X ECEF. All of you remember it. Okay. Now by using right hand thumb rule, it will be YECEF. This is the fourth coordinate system. Okay. Now we'll see the raw measurement that is collected by the laser scanner unit in terms of range and scan angle. How it is transformed by combining the measurement of IMU, GNSS, as well as some calibration parameters to transform this coordinate of point P from this instrument reference system to this ECEF, this vector. Okay, see carefully. Okay. T is equal to T1. The laser beam is fired. Okay. And if you see the coordinate system of instrument reference system, so it is like that. You can do it in red color. Okay, so this is X, Y, and Z. Instrument reference system, IRS, and for point P, the raw measurement is R1 and angle θ1. θ1 is a deviation over here. This is called as scan angle. What is the deviation of this laser vector? This laser vector from ZIRS, that is given by θ1. And R1 is the range, this value. So how we can proceed? What we do, we assume an instantaneous coordinate system. See, we assume over here an instantaneous coordinate system which is having its z-axis towards the laser vector. Okay. So z-axis is towards the laser vector. Fine. And all other, in that case, what will be the deviation of x? So z instantaneous, actually what we are doing, z IRS, we are shifting along the direction of laser vector corresponding to time t1 for point P.
Sir,
Mm-hmm.
sir, no, sir. Sir, just like 2 minutes, I was disconnected from the class. Can you repeat the
No,
question?
no. Who's there, Sumit?
No, sir, Bhagat.
No, fine. We have discussed about that. Okay. So the z instantaneous, which we are defining over here, so we are considering the vertical plane. Listen carefully. This is the vertical plane. And this x IRS is perpendicular to the vertical plane. And you can see this laser vector is in vertical plane. So this is y IRS. So the two axes, y IRS and z IRS, they are in the vertical plane. What happened in the same plane? Laser beam is fired along some other direction, and it is hitting somewhere here over point P. Point P is located over here. Okay. Now what happened? We are considering this direction. We are defining an instantaneous coordinate system where z-axis is along the laser vector at time t1. So that is z instantaneous. So what will happen in that case? The y instantaneous will also be rotated. This will be y instantaneous in the same plane. But there will not be a change in x instantaneous. So this x instantaneous will coincide with, these two are parallel. Because see, in a particular plane, in one particular in a swath, all the laser beams are fired. Okay. What we are doing over here, in a vertical plane, the y IRS and z IRS are defined. Okay. X IRS is perpendicular to that plane. For a particular laser, this laser footprint corresponding to point P, we are defining an instantaneous coordinate system where the z instantaneous is considered towards the laser vector. Okay. So similarly, if it is rotated, this x IRS is, you can say this axis is rotated by angle θ1, that is given by the scan angle. Just see, I'm talking about this angle. So this angle is calculated θ1. And what we are doing, we are considering along the laser vector the z instantaneous. So obviously there will be rotation. It is rotated, then there will be a same kind of angular separation between y IRS and y instantaneous. But x instantaneous is parallel to the x IRS. What does this mean? It means the instantaneous coordinate system. You rotate the instantaneous coordinate system by angle theta in anti-clockwise fashion, then z instantaneous coincide with z IRS, y instantaneous coincide with y IRS. So rotation has to be performed about x-axis. What will be the coordinate of point P, okay, in instantaneous coordinate system? Who will tell me? Instantaneous coordinate system is towards the laser vector. And for the given laser vector, R1 is the distance it is measured. So what will be the coordinate of point P in the instantaneous coordinate system? We have already done the conceptualization of all these problems, and we have even discussed about them. Just you need to apply those concepts over here. See, from the laser scanner origin to this point P, the distance is measured R1. The z-axis of instantaneous coordinate system is considered towards the direction of range measurement. Okay. So what will be the coordinate of point P in the instantaneous coordinate system? Salja, could you please unmute?
Yes, sir.
Okay, so please tell me what it will be.
Sir, I'm not able to understand.
Okay, please mute. दो मिनट का टाइम मैं दे रहा हूँ आप लोगों को. Just recall all the concepts and let me what it will be. आलोक म्यूट करो अपने को।
यस सर।
हाँ, अब बताइए, ये क्वेश्चन समझ में आया?
सर मतलब इंस्टेंटेनियस कोऑर्डिनेट सिस्टम में एक IRS है और P की कोऑर्डिनेट वैल्यू बतानी है इंस्टेंटेनियस में।
हाँ, यहाँ पे देखो दो कोऑर्डिनेट सिस्टम है, एक तो ये है कि इंस्ट्रूमेंट से एसोसिएटेड है, दैट वी हैव ऑलरेडी डिफाइंड ओवर हियर, फाइन।
ठीक।
और दूसरा ये है कि इंस्टेंटेनियस कोऑर्डिनेट सिस्टम हमने एक एज्यूम किया है, और इंस्टेंटेनियस कोऑर्डिनेट सिस्टम की जेड एक्सिस इट इज टुवर्ड्स द लेजर वेक्टर।
ठीक है।
ठीक है, लेजर वेक्टर का मीनिंग ये है कि जिस डायरेक्शन में वी आर मेजरिंग दिस r1। ओके,
यस सर।
so it is a case like, just see over here, it is x instantaneous, y instantaneous, and this is z instantaneous. Okay,
यस।
and we have a point over here p, this is origin O, this is measured as r1. What will be the coordinate of p in the instantaneous coordinate system?
So 0 0 R1.
Correct. Okay, so this is like, just see z, this is measured along z instantaneous, so the coordinate of point p you can mute. Okay, so we can write over here the coordinate of point P in instantaneous coordinate system. Okay, it will be it can be given by the row vector 0 0 r1. Okay, if you want to measure it in a ZIRS, what should be done? You need to multiply it by a rotation matrix that is about x-axis by angle θ1. Okay, so see, if you rotate it in a counterclockwise by angle, this is the θ1 we have measured, we call it scan angle. Okay, so if it is θ1, fine, then what will happen? The θ1, and if you rotate this z instantaneous about x-axis anti-clockwise direction, then it will coincide with ZIRS, and similarly y instantaneous coincide with YIRS, and XIRS is already parallel to the x instantaneous. What it will be? The point P coordinate in instrument reference system is equal to it is multiplied by Rx by angle θ1. Okay, now just see, so we have calculated point P coordinate in an instrument reference system. Now we transform this vector from instrument reference system to IMU body coordinate system. And we have seen that This is the direction of flying aircraft nose. We have a XIRS with little offset. We have a XIMU. Similarly, the right wing towards right wing we have YIRS, and downside we have a ZIRS. Here we have YIMU towards the right wing of flying aircraft, because this is pitch axis. Okay. Z will be somewhat downward because this is axis. ZIMU. So we have the angular biases between these axes are computed in terms of alpha naught, beta naught, and gamma naught. These three are the angular biases, and they are fixed. Because see, IMU laser scanner are rigidly mounted and they are integrated with the flying aircraft. So there is no relative movement between the IMU and laser scanner. So these angular biases, you can see they are fixed once the sensors are installed. Alpha naught, beta naught, gamma naught are the fixed values. They do not change with respect to time. They are calculated by calibration. We'll discuss about it. They are not measured by any sensor, because these alpha naught, beta naught, gamma naught, they are related with how we install the sensors. Okay, so they are the calibration parameters. And if you then what we do, we again multiplied this vector. If you want to measure this vector point P in IMU body coordinate system, but origin at instrument reference system. Just see, listen carefully. We are rotating the axis of instrument reference system by alpha naught, beta naught, and gamma naught to match the axis of instrument reference system with IMU body coordinate system axis. So in that case, what we can see, the point P is now in the vector, the coordinate of point P is in IMU body coordinate system, but we are not shifting the origin. Origin is still at instrument reference system. So this vector is given by what we should write over here. What is the multiplicating factor? We rotate about x-axis by alpha naught. 3 rotation has to be performed. Rx by alpha naught. Beta naught and Rz by gamma naught. Okay. So alpha, beta, and gamma naught are the rotations required to match the axis of instrument reference system with the IMU body coordinate system. Now this vector tells us, okay, now this point P is over here. This point P is in IMU body coordinate system, but origin still lies over here. So this is a kind of vector from this point to this. So origin of IRS instrument reference system to point P. If you connect these two lines, you get this vector, okay, and it is in IMU body coordinate system. I'm again giving you 5 minutes time to think about it and let me know if it is not clear to you.